Okay, this is Mickey Josie. Welcome to my math class. It's day 1 and we're talking about the birthday numbers. Okay, so the birthday numbers are a little thing that I use to guess your birthday. So tell me, yes or no, is your birthday on this page? Tell me. No. So they say no to this page. So what we're going to do is we're going to throw out the number 1. We're looking at this top corner number. And since they said no to this page, we throw out 1. Is it on this page? So since they said yes, we're going to keep the number 2, throwing out, yeah, so in our minds we're thinking number 2. Okay, is it on this page? No. We look at this corner number 4 and we throw it out. He said no. What about the last page? Or no, the second last. This is also a no, so throw out the number 8. And what about the last page? Yes. So since we said yes to the page that had the 2 in the corner and the 16 in the corner, we're going to add 16 plus 2 and we get 18. Now let's look at this pattern, because why does this even work? And this will work if you say yes to the page, you're going to add the corner number. If you say no to the page, you're going to throw it out. Let's look at that pattern. So what number appeared on the first page in the corner? 1. What was the number that started the second page? 2. What was the number that started the third page? It was 4. And the next number was 8. And the last page started with a 16. Can anyone describe what this pattern is? Oh, the numbers are doubling. The numbers are doubling. Okay, what would the next number be if I had another page? Okay, and then followed by, and then, and then, and then, close, and then, okay, and this pattern can go on for infinity. In fact, if you get into math classes where they talk about different kinds of patterns, we call this a geometric pattern. And the reason why it's a geometric pattern is because the rule is, what are we doing to the number to get the next number? We are doubling. What's another mathematical, like when I say I doubled something, what did I do to it mathematically? I multiplied it by 2. So if you're multiplying by the same number every time, then okay, that's the that's the same thing as doubling, okay? So we're multiplying by the same number every time. This number pattern could go on for infinity. Why did we stop at 16 in our pages, do you think? Why didn't I have another page that started with the number 32? Oh, there's only 31 days, right? Now, what would happen if a person said yes to every single page? What day would they be born if they said yes to every single page? And what would you do to find out? It would be 1 plus 2 plus 4 plus 8 plus 16 equals 31. If you add 1 plus 2, you get 3. Notice that 3 is the number right before 4, right? If you add 1 plus 2 plus 4, you get 7, and 7 is the number that happens right before 8. What do you think that 1 plus 2 plus 4 plus 8 add up to? Yes, because that's the number that comes right before 16. Now, so that's kind of awesome. There's a special name for this kind of pattern since we're multiplying by 2 every time, and it's also called exponential growth. That's because When you multiply by 2 repeatedly, you can use an exponent. Does everybody remember this exponent, 2 to the first power? What would that be? 2. What about if I go 2 times 2, I multiplied by 2 to get 4, so 2 times 2 equals 4, but that's the same thing as 2 to the what power? 2 to the second power, okay? I wanted to put it here, I guess. Okay, 2 to the first power equals 2. Now I did 4 times 2. Well, 4 is 2 times 2, so isn't this the same thing as 2 times 2 times 2 gives you what? 8. Oops, I meant to put 8 over here. Okay, what exponent would I use here? 2 to the third power. Does everybody see why that would be the same thing as 2 to the third power? Okay, what do you think about the number 16? I have a 2, here's 8. 8 times 2 equals 16, right? But 8 was 1, 2, 3 2's. So if I multiply by one more 2, I'm doubling that number, right? This number right here was 8, and I double it. Here's 8, and I double 8. If I double 8, I get 16. What's another way of writing 16 using the powers of 2? 2 to the fourth power. Okay, then 2 to the fifth power. What do you think 2 to the fifth power is going to be? 32. 2 to the sixth power is going to be 64. 2 to the seventh power is going to be 128. 2 to the eighth power would be 256. Okay, and then what about this one? If I were to use this pattern and go backwards, 8, 7, 6, 5, 4, 3, 2, 1. What comes before 1? 0. What is 2 to the 0 power equal to? It's equal to 1. Okay, and you can put any number to the 0 power on your calculator. I didn't bring my calculator up here, but you can take 2 to the 0 power. This is essentially the essence of your computer science language, which is binary code. Binary code is all about yes, no, yes, no. Zeros are no. Ones are yes. So if you want to write the number, well, I don't know too much about binary code. This is my computer science friend who is a teacher. Shout out to Teddy Chow. He taught me this, just so I could teach you how the birthday numbers work. But essentially, every time you say yes or no to a number, that's corresponding to those zeros and ones. That's why you notice if you have an iPhone, or actually probably any phone for that matter, do you have a size 8 or a size 16? Or do you have a size 32? Or do you have a size 64? It's the same thing with your flash drives, right? I could buy a size 64, but the next size up from that is going to be a 128. That's everything to do with exponential growth, and what we call these are called powers of 2 because they have an exponent. So powers of 2, and it's the basis of binary code. So if you want to make millions being computer scientists, you will get very familiar with this pattern. So that's kind of the main reasons why I'm bringing up the pattern. It's also because the most exciting thing to me about math is patterns, okay? I don't want you to, I don't get excited about like multiplying 4-digit numbers, or like decimals. I don't want to do long division of decimals. That's not fun to me. What is fun to me is being able to have strategies and mental math so that it's like, oh, the patterns of math are so cool. And number patterns are really what make us really kind of enjoy math, for those people who can recognize a pattern. And that's really the big goal here, is to be able to recognize patterns, describe patterns, and even to put algebra. Y equals 2 to the x would be the equation for the exponential growth for a power of 2. And you will actually get into that in math. You're right now in Math 65, but you will get into that in Math 111. We'll talk about exponential growth, and even in Math 95. So there's some advanced math. Also, there are, I am going to give you guys a list of books, math books for kids. If you don't have it, email it to me. Email me, I'll send you the list, okay? I'm going to give it out if you want it. There's a couple of books that explore this pattern. One is called A Grain of Rice, and another one is called The King's Chessboard. But they're basically dealing with the fact that what happens to numbers when we double them? They get really big really fast. And the graph is not a line. It will look something like this. And it actually even is more steep than that, probably. That's just a little quick sketch of what it looks like, okay? So any questions on that? Yes. We're going to get there. Yes, 2 to the 0 power is one. That's actually a really big concept that we're going to explore in more depth. It would take too much to go into it right now, but we will definitely be learning it in this class when we're going to be dealing with laws of exponents, which are going to get into this very number. It's going to get into patterns and how exponents work, but it's a pretty long explanation for this moment, okay? Yeah, but good question.